Hello, my name is Nitin, and I am here to present IoT-based AQI estimation using image processing and learning methods. With me on this paper are Patwardhan, Jayati Narang, and Sachin Chaudhary. We all are from Signal Processing and Communication Research Center, IIIT Hyderabad, India. Okay, so let's start. So the flow of this presentation is as follows. We'll talk about the motivation first, why we started. Okay, then what are the contributions that are present in this paper? How did we set up the hardware? How did we collect the data set? What were the method that was proposed? The results that we got for that method? And finally, what is the conclusion? So starting with motivation. We all know that air pollution monitoring is an essential task, right? We must know that the air we breathe in, how good is that air, right? And there are good quality air pollution monitoring stations in the city. There are electronic gadgets for air pollution monitoring that are available. However, they demand maintenance, right? So the idea here is that to build an IoT-based device to monitor the air quality index with the help of images and learning methods. So what we are trying to achieve here is that for a given traffic scenario, we're trying to estimate the AQI, right? Using the images and other weather parameters. And the AQI estimation should be accurate, robust, and dynamic in nature. So when I'm saying dynamic in nature, the stations are stationary, right? So we are looking for some device which is portable, which is dynamic, right? Which can go from one place to another place to get the AQI and still accurate and robust. And in addition, having an image-based AQI allows portability. So for example, you have a smartphone, you just click the image and then image of a traffic, and then you get the AQI, right, in real time. So that's the main motivation over there. Okay, so let's start with the contribution. What are the contributions of this paper? So we are saying that we have contributed IoT-based methodology to estimate the real-time AQI into 5 different levels, right? Using traffic images and weather parameters. So an entirely new traffic data set was collected on Indian roads containing almost 5K images and related weather data with co-located ground truth PM values. When we say co-located, that means when we got the image, we got the PM for that particular location, and not just the PM values, but the other weather parameters as well. So the dataset contains samples across the Indian city of Hyderabad in different seasons. Okay. And the methodology that we have proposed is achieve overall 82% accuracy, considering the PM variation due to the season. So the PM values changes from season to season, right? In winter, it is in general more compared to other seasons. So we saw a significant improvement in the accuracy of AQI estimation when we compared with the existing work. And then we will talk about it in detail. Okay, so let's talk about the hardware setup that we made. So you can see this image. In this image, you can see there is a prana air sensor, right? This is part which is used to capture PM 2.5 and PM 10. There is a BME 280 to get the humidity and temperature. This whole circuit has a Raspberry Pi MCU to do all the computations and to send the data to cloud as well. There's a Pi camera attached to get the images. And this whole thing is enabled via 4G cellular Wi-Fi AP to send the data to server, making it suitable for each computation. Coming to the dataset collection part, how did we collect the dataset? So what we did with the help of the hardware setup that we had, we mounted that setup on top of a car, right? Okay, let me just put this a little bit up. Yeah, we mounted it on top of a car. And we roamed in the streets or the roads of Hyderabad, right, containing the images of traffic and the measure of pollution levels along with the weather parameters. So you can see this map shows that these are the blue lines that we traveled across months to get the images and to get the respective AQI values, the PM 2.5 and PM 10. So a total of 5K images were captured during daytime. That includes variations like different scenarios of traffic, urban and suburban. There were various traffic conditions, right? Low traffic to high traffic. There were low to high pollution levels. And we record the data set for 2 different seasons, monsoon and winter. And each captured image is associated with co-located respective sensor values. So when we say co-located, for each of the image, we have the corresponding PM 2.5, PM 10, we have the temperature, and we have the relative humidity. Okay, so from the PM 2.5 and PM 10, we computed the AQI value as per the Central Pollution Control Board, India. And we categorized the AQI value in 5 different classes. And these are as follows. So let's say the AQI value is between 0 to 50. The category is good. 51 to 300 satisfactory. 101 to 200 moderate. 201 to 300 poor. And if it is more than 300, then it is severe. This graph shows that the distribution of AQI levels in the captured dataset. So we can see here is that we have, so in out of total 5,000 images, we have 1,000 images which contains in the good category, around 1,500 for satisfactory and moderate, and around 500 each for poor and severe. We have less poor and severe because that condition occurred very less compared to other when we were roaming in the streets of Hyderabad. And this graph shows that for which month we got how many samples. So September, we got around 1,600 images, 1,600 samples, you can say. In October, we had around 700. And again, in November, we got around 1,500, 1,600. And then in December, we had around 800 images. So in total of 5,000 images. Okay. So the dataset collection part is done. Now the methodology that we propose to estimate the AQI. So the figure here shows the whole pipeline of this. So given a traffic image, you can see we are applying YOLO V5, which is object detection and localization algorithm, to detect the vehicles present in that image. So you can see, we can see a car here as being localized, and then auto, and then car, bike, all vehicles are being recognized here. Another thing that we got from this image is what is the visibility score of the image. And then I'll come to the detail why the visibility score is needed. Right. And so these are the image features we got, right? And then we got the, from sensors, we got the temperature, we got the humidity. And from PM 2.5, PM 10, we got the AQI level, which is acting as a ground truth. So we have the feature vector coming from the images and sensor, right? And then with a corresponding AQI level. And this whole task boils down to a supervised learning problem for which an ML model can be trained for 5 different classes: good, satisfactory, moderate, poor, and severe. So we'll talk each part in the detail in the upcoming slides. Okay, so let's start with image feature extraction. How did we extract the feature from the image? Okay, so given any traffic image, we simply used a YOLO V5, which is an object detection and localization algorithm. And we detected all the vehicles present in the image, right? And their count, how many of them they are, and the type of the vehicles, right? And to detect the vehicles, Euro V5 algorithm was trained for 25 epochs on Indian driving data set. And the number of classes and the number of vehicles that actually we were detected is that motorcycle, car, truck, bus, and auto rickshaw. Okay, so what is an IDD? What is an Indian driving data set? Indian driving dataset is an object detection and localization dataset that includes images covering Indian highways and lanes with various traffic scenarios and illumination conditions. So this dataset got public around a couple of years ago, okay? And it contains the images and their annotated bounding boxes, okay? It's publicly available and you can go and check out Indian driving dataset, okay? So this was easy. We trained a YOLO V5 model. Next is from the traffic image, we got a visibility score. And the visibility score is necessary because it captures the air pollution generated by the other sources, such as, let's say there are some construction going on, roads, buildings, or some fire somewhere there, right? Because the camera is only seeing to the straight, is not able to capture what's happening in the 360 degrees around. So it's necessary to capture the haziness, the visibility of the image, right? To find if the image is visible or not. If image is less visible, that means there are other factors which are contributing to the air pollution. And to get the visibility score of the image, we simply use the BRISC algorithm, which is a no reference image quality assessment metric. This paper, BRISC algorithm, came out way back in 2008, simply used to get the haziness of the image, which we are using as a visibility parameter. So what BRISC algorithm gives us? It gives us a number between 0 to 100, where 0 says the visibility is best and 100 says the visibility is worst, right? As you can see here, for this particular traffic image in a sunny daylight, it's saying the visibility score of 35, which is more what visible. Okay, coming next. So how did we generate the whole dataset metrics? So for any given example, we have image features, right? So all the vehicle count are there, and then we have the visibility score. We are the sensor features, temperature and relative humidity. And for each of the feature vector, right, we have a corresponding AQI level coming from PM 2.5 and PM 10. So for a given sample, there are 6 image features, right? 2 sensor features, temperature and relative humidity, and the corresponding ground truth AQI level compared using PM 2.5 and PM 10. So for a given sample, we have a M cross 8 sized feature vector, right? And where M is the total number of samples, in our case, around 5K, right? So we got this whole matrix, right? And there's a M cross 1 sized vector Y, which contains the corresponding labels. So this whole problem now boils down to a supervised learning problem, right? Where we have the features, we have the labels, and then we have to identify the classes, right? Where the classes are AQI levels. Okay, so how did you train the ML model? With the help of the feature matrix M and the corresponding level vector Y, the ML model was being trained to detect the 5 different AQI levels, right? And because there are different ranges of values, right? It was necessary to normalize the dataset. So we simply used a standard normalization to ensure 0 mean and unit standard deviation. Further, we used something called k-fold cross validation, where k equal to 10, to make sure that the model is generalized well, and to minimize the occurrence of bias estimation than compared to the normal train test split, right? And we tried with 3 different ML models that were experimented: random forest, support vector machine, and multi-layer perceptron. For random forest, we chose the number of decision trees set to 100, and the split criterion was set to entropy. For SVM, we used as RBF kernel with regulation parameter set to 5. And for MLP, we used 3 hidden layers, each having 20 neurons with ReLU activation function. So we basically tried with different parameters, and then we boiled down to this particular number. This was performing the best. And all the above models are classification-based ML models, supervised learning problem, where the number of classes were set to 5, depicting each of the AQI level. Okay, so when the training was done, now the part of the detection. So at the time of detection, so we use this particular train model to estimate the AQI for a given image. So for a given traffic location, firstly, the Pi camera captures the image, and the image is passed to YOLO V5 and BRISC algorithm to get image features. The sensors provide the corresponding temperature and humidity values, right? And now we see the number of features from the image. We are getting 6 features. From sensors, we are getting 2 features. And in total, we have 8 cross 1 feature vector, right? Which is passed to the train ML model. And in general, and in turn, it gives the AQI level estimated. One thing to note here is that all the computation related to AQI estimation, for example, running YOLO V5 to get the number of vehicles and their type, to running the BRISC algorithm to get the visibility, and finally running the ML model to get the AQI estimated, are all performed on the Raspberry Pi Zero MCU itself, right? And only the estimated AQI is sent to the remote server, making it suitable for edge computation, right? So all the computation is only happening to the Raspberry Pi, and we're only sending the estimated AQI. Okay, so we talk about the results now, these proposed methodology. So let's start first with the ULOV5 model results for vehicle detection and in road scenarios. So this figure shows you the metric on which the ULOV5 was trained. We can see the x-axis is representing that how many epochs that we ran for. In total, there are 25 epochs. The precision we got is 86.54% of 0.47% recall and 53.75% mean average precision. Okay, this shows the R2 score of the features. That means with respect to the AQI levels, how the features are varying. And when we talk about the features here are vehicles combined, temperature, humidity, and visibility. Okay, and we see that all the features have a positive correlation with the AQI in the range of 0.2 to 0.4. This indicates the partial dependence of the AQI on these features. So these are all saying that these features are playing some important role towards estimating the AQI. Okay. So let's talk about the results of the ML model. So the ML models were trained and validated for the dataset that we mentioned, right? Because there are seasonal variations in PM values that we discussed earlier, there are 3 different ML models were trained, each for 3 types of dataset: monsoon dataset, winter dataset, and overall dataset, like where the monsoon and winter dataset is combined. Okay, so this shows the table for the accuracy. We see that the random forest model performs best for all of these, for monsoon, winter, and overall. For monsoon, it got a 0.9% accuracy. For winter, it got 0.8% accuracy. And then for overall, it's 0.8 accuracy, right? And the monsoon is better, mainly due to the better training of the model, as there are high number of data points with low AQI values in monsoon season. And the most of the data points lies in the first 2 categories itself, good and moderate, right? So the model task got easier when we trained for the monsoon dataset. However, for the winter dataset, because the pollution is more, the PM was actually spread for over all the classes, right? And then we got an accuracy of 82%, which is relatively low from the when compared to monsoon, because the data is spread over, the AQI level is spread over all the 5 classes, and which increases the chance of misclassification by the model. But yeah, overall, we are getting 82% accuracy. And when we compare this with another method that was proposed by Chakma et al. In ICIP 2017, and what they did is that they took the image, they simply passed that image to a plain CNN to estimate the AQI levels, right? So what we did is that we applied their methodology on our data set, and then we observed that our method has an overall accuracy improvement on 15% when compared to their method on our data set, right? And the main reason that there is an improvement because how the features from the images are being extracted, right? Because when you see the image of a traffic, right, there are many other different objects, right? For example, there are pedestrians, right? There are cyclists, and they are not part when it comes to the air pollution. They are not contributing anything to the air pollution, right? So our work emphasizes focusing only on those responsible for air pollution, right? On the other hand, applying plain CNN on the images straightforward fails to identify this paradigm that which particular object is contributing to the air pollution, right? Okay, so there is the paper link. You can go ahead and read their paper as well. So what is the final conclusion over here? So we are proposing a simple yet effective image-based AQI estimation technique on an IoT device using a mixture of machine learning and deep learning supervised learning algorithm. The experimental result shows that accuracy up to 90% for the AQI classification for monsoon, but an overall of 82%. Currently, the work is limited to predicting the AQI only under daylight setting, and the authors plan to scale it to nighttime as well, as to collect the data for the summer season as well, right? Authors also plan to gather data and predict AQI for different cities as a future work. So right now we, as a prototype, implemented on the Hyderabad roads, but can be implemented for other cities as well, not just in India, outside, anywhere as well. Right? Thank you so much for listening this out.